Okay, so in today's section, we will discuss about ionization energy from an emission spectrum. Ionization energy from an emission spectrum. This is purely an HL part, so let's discuss about it. So let's talk about what is emission spectrum. Or emission spectra. So hope you all are aware that when, let's say, this is an nucleus and this is the first cell. Let's say this is n equal to 1, this is the second shell, this is n equal to 2. So let's say there is one electron. So when electron gains energy, it jumps from n1 to n2. Here the electron is, and when it returns back, let's say it's coming back, at that time it releases some kind of energy, right? That energy is photon actually. Photons are released. Packet of energy is released when it come back. So electrons, they keep on moving. So this is emission spectrum. When they are coming back, they release some kind of energy which is called emission spectra. So electrons, let's write some points about it. So electron move rapidly around the nucleus shell, nucleus in shell, right? And now how the electrons will get excited? Either you can give heat or you can give electricity. Can be used to excite an electron, and when they get excited, they go to higher level, to a higher main energy level. So let's say, what is range? So range is n equal to 1, which is a ground state, and they move to n equal to 2, which is an, let's say it is infinity, maybe 2, maybe 3, maybe 4, right? So when electrons fall back, right, when they are returning, so when the electron return, right, they must lose the energy. This is very important, because when they are going from the next to the next level, they are gaining energy, that's why they are going. But when they have to come back, they have to release that energy, right? So when the electron returns, they must lose the energy difference between the two shell. Right? So this is important. So this loss of energy is released like a electromagnetic radiation, and it may be infrared, maybe visible light, maybe violet light, right? So this loss of energy is performed by releasing electromagnetic energy in the form of either infrared, or we can say visible light, or you can say UV light or UV radiation. So any form it may be, right? But the big question is, when the electrons are returning, like coming back to ground state, the energy released is always UV light, ultraviolet region. So you can say when electron return back to n number 1, right, the energy is UV region, and this is correspond to Lyman series. If you remember, we have discussed hydrogen spectrum. So these are the Lyman series, right? So if you remember, let me give you a few ideas. If you've gone through my previous videos, you will get. So Lyman series was coming when, let's say, this is the first cell, n is equal to 1, this is n is equal to 2, this is n is equal to 3, this is n is equal to 4, this is n is equal to 5, this is n is equal to 6, right? Like this was there. There's so many. So if electron jumps from, let's say this is n equal to 7, right? So if the electron jumps from either 7 to 1 or 6 to 1, 5 to 1, 4 to 1 or 2 to 1, it was a Lyman series, right? When electron jumps from 7 to 2, 7 to 2, 6 to 2, 5 to 2, 4 to 2 or 3 to 2, it was Balmer series. When electron jumps from 7 to 3, right, or 6 to 3, 4 to 3, it was Bastian. When electron jumps from 7 to 4 or 6 to 4 or 5 to 4, it was Bragg series. And the last, when electron jumped from 7 to 5 or 6 to 5, it was P-fund. And what we have seen, Lyman is ultraviolet, Bragg is visible, Bastian is infrared, IR, Bragg is also IR, P-fund is also IR, right? So if I'm, so this what gives, this gives an evidence for Bohr model, which is an idea that electrons exist in discrete energy level. So exact amount of energy is required for an electron to jump, and an energy level to a little like a ladder, right? So we can say that this gives evidence for Bohr's model, which is the idea that electron exist in discrete energy level. So an exact amount of energy is needed. for an electron to jump and energy level a little like a ladder. So they are moving. So however, there are limitations in this model. Limitations. What are the limitations of this model? First limitation was assume positive of electrons are fixed. Then only assumes positive of electrons are fixed. Second assumption is assumes energy levels are spherical in nature. Assume energy level are spherical in nature, right? Third limitation, Bohr limits calculation to hydrogen only, right? That's a limit calculation to hydrogen only, right? So does not explain the line of spectrum of other elements containing, let's say, more than one electron. So that was a bit difficult for the Bohr model to explain it. So the concept of limit of convergence has come. Let's talk about the limit of convergence. What is this? Limit of convergence. As a line spectrum is produced, the line becomes closer together, right? So they come nearby. So where the lines appear to meet is called limit of convergence. So as the line spectra is produced, the lines will become close together, right? So where the line appears to meet is called limit of convergence, right? So the convergence limit is the frequency at which the spectral line converge. When we say convergence, so convergence limit is frequency at which spectral line converge, right? So the energy required for an electron to skip the atom or reach to the upper limit of convergence is the ionization energy. So we can say that the energy needed for an electron to skip the atom is ionization energy, right? So the frequency of the radiation in the emission spectrum or the limit can be used to determine the first ionization, right? So we can say the frequency of radiation in emission spectrum at the limit of convergence can be used to determine ionization energy 1, right? Let's discuss about some formulas, how we can do that. So in the Lyman series, what we have seen just now, let me go up and show you the Lyman series. So in the Lyman series, we have got a series of bands, right? So if I have to put like this, I will get a line. Like I'm getting lines like this. Right? Two lines here. I'm getting one line here, one line here, one line here, like this, right? So this is your Lyman series. Right? So how to calculate first ionization? Let's talk about that. Okay. Calculating ionization, first ionization energy. So when detailing the Lyman series, the largest transactions represent the fall from infinite level and 1. So in reverse, it can be considered to be equal to ionization energy, right? Therefore, the first ionization energy, that means ionization energy 1 of an atom can be calculated uh, using the frequency. When we say frequency, we can say wavelength lambda of convergence limit. Now when I'm saying this, so we have a formula, delta E is equal to h mu. And if I'm going to, in order to calculate the first ionization energy, we must calculate frequency using the given data, right? So C is equal to V lambda. So V is equal to C by lambda. And once you know the frequency, you will able to calculate. Once we know the frequency, we can use this to calculate ionization energy, right? So where E is equal to energy in joules, H is a Planck's constant. Planck's constant has a value 6.63 into 10 to the power minus 34 joule second. Sorry. V is your frequency retained per second. Lambda is the wavelength in meter. C is speed of light, which is 3 into 10 to the power 8 meter per second. Right? With this, we can able to calculate. Let's discuss one question on this. Let's say the question is the convergence limit for sodium has a frequency, let's say frequency of 1.2 into 10 to the power 15 per second, right? Now calculate first ionization energy of sodium in kilojoule per mole. So now how to solve this? How to find the solution for this? We have to calculate ionization energy. So first we know delta E is equal to HB, right? Now what we have to do? Substitute the number from question and data booklet gives energy change per atom. So for the first ionization energy, we will get 6.63 into 10 to the power minus 34, and this is I'm getting 1.24 into 10 to the power 15. Sorry, it's 1.2 into 10 to the power 15. So first ionization energy I'm getting 8.22 10 to the power minus 19 joule per atom. Now calculate the first ionization energy per mole. So multiplying by Avogadro number. So when I'm going to multiply with Avogadro number, so this will be multiplied with 6.02 into 10 to the power 23, which will come around 494.916 into, let me convert. So I'm getting 494.916 joule mole inverse. Now we have to convert joule into kilojoule. So that means divided by 1000. So I'm going to get 495 kilojoule mole inverse. This is the answer. So this is how we can find the question, find the solution for the first ionization energy based on convergence limit frequency value. So in the next lesson, we'll discuss more about it. So far, that's it for today. See you in the next video.